Okay, we study X15NQ. This is elementary material. You do not have to study if you are familiar with any basic concept introduced in X15Q. Discuss the conditions of the equilibrium of a rigid body. Okay, let us consider a rigid body of mass m distributed over some finite volume under uniform gravitational field. In a constant gravitational field with a gravitational acceleration g, a point mass m experiences the gravitational force. That gravitational force is the net force on the system and will be mg. That's fine. In the same situation, on infinitesimal mass, if it is uniform material, consists of uniform material of density rho, it should be total mass m over volume. And if it is a very tiny piece, the mass over total mass should be volume divided by total volume. So dm should be v over m, m over v, the volume element. And this is a density, so it can also be written so g times the dm, this rho, this volume, infinitesimal volume, is not a vector but product of dx, dy, and dz, and it is actually displacement vector along the x-axis, displacement vector along the y-axis, and displacement vector along the z-axis, cross product, scalar product. This is a triple scalar product to represent the volume element, infinitesimal volume element, spanned by dx E1, dy E2, and the z E3 hat. And volume of this parallel pipe is a triple scalar product, and that is d cube x. Okay. The net gravitational force applied to a rigid body can be integrated as the gravitational force applies to a small element, and we sum all of the forces. So this small amount is called the F at position x. So this will be summed as an integral, and if I substitute this differential force element, GDM, we can express like that. And because this acceleration is a constant, so we can factor this vector out of the integral, and we are left with the integral mass or integral density volume. And actually, because G is factored out, it is nothing but the total mass of the rigid body. Therefore, the trivial integral has been carried out to find out the gravitational force, net gravitational force applied to a rigid body is mg. Here the constant vector g has been factored out, right? So because it is independent of the variable m. The center mass of a rigid body with mass m is defined by this one, weighted average of the position. Here, m is the integral of the differential mass, so total mass of the rigid body. So center mass is weighted average of the position vector with the weighting factor mass. Let's see, if I multiply both sides by the total mass, what I obtain is integral of x over mass is total mass multiplied by the center of mass. Okay. The net torque applied to a rigid body can be integrated as, okay, net torque due to the gravitational acceleration and gravitational force. Torque is integral of small torque. This is a rigid body, and this is a small amount of mass. This is a center of mass. Here, x times force. X cross force is the torque. So this differential torque on a small, tiny, infinitesimal mass element due to the gravitational force applied is x cross df. And we recall that the f is the constant gravitational acceleration multiplied by the differential mass. We substitute this one for df. Again, we find that this g is a constant vector, and this is a scalar. We can make a commutation. This is commutative. This mass is commutative. So bring it inside, and cross product with the gravitational acceleration can be pulled out of the integral. And this cross product is not commutative. We must not exchange the order. So cross g is still on the right hand side. By the way, integral of x dm, that is by definition, we have mass times gravitational total mass times center of mass. So I have mass, total mass times the center of mass cross product with the gravitational acceleration. Now mass is commutative. I can bring it in front of the gravitational acceleration. And what's that? This is the gravitational force applied to the whole rigid body. Here, what I find is the torque, net torque on the system is nothing but the gravitational force is applied, and there is XCM. If it is a reference point, center of mass is there, and torque is applied, effectively applied in such a manner that the whole gravitational force is applied to a single point, that is the center of mass. So if I choose the point at which the torque is measured at the center of mass, then there is no torque. So if I have an axis of rotation that passes through its center of mass, then under the constant gravitational field, a rigid body does not rotate. In addition, if we hold some point that passes through the center of mass, then I can always make an equilibrium by canceling the gravitational force, sustaining the gravitational force mg by minus mg. In addition, if I hold this with the minus mg, there is a net torque appears. So gravitational force applies to the center of mass. My sustaining force is sustaining the gravitational force by exact amount with opposite direction. However, because of the difference in non-vanishing lever arm, it automatically rotates, so torque does not vanish. In order to make a rigid body in a complete equilibrium, I have to sustain the point at the center of mass at least along a straight line that passes through the center of mass. Only if torque is zero, torque net. This torque net is the algebraic sum of the gravitational torque and my sustaining torque. F net equals zero, algebraic sum of the gravitational force and my normal force or any constraint force to hold it. So torque is X cross F, and this one shows that the torque due to the gravitational force is effectively acting at the center of mass. We have equations of motion for linear version and rotational version. Linear version is the time derivative of total linear momentum and time derivative of total orbital angular momentum. They are net torque, they are net force. Okay. The total linear momentum of a rigid body can be computed. So total linear momentum is the sum of a small linear momentum, and small linear momentum means small mass multiplied by its velocity. Okay, so we have x dot dm. This is a time derivative. I can pull this one out, and this is an integral. What's that? This is nothing but the mass times center of mass. So if we ignore the special theory of relativity, mass is invariant. So in Newtonian mechanics, mass is invariant. So in that case, I can take the derivative of the center of mass only. So the total linear momentum of a rigid body is the total mass multiplied by the velocity of the center of mass. As a result, if I take another time derivative, I have time derivative of the total linear momentum, and then still the total mass is invariant. In that case, I have mass times the acceleration of the center of mass, and that is the net force applied to the system. Remember, the net force applied to the system is exactly the same as a net external force applied to the system, because any interaction between any two objects inside the system in here is the rigid body, cancels because of law of action and reaction, Newton's third law. We recall that the lever arm vector relative to the axis of rotation, if I have an x, the axis of rotation, and this is a parallel component, and this is perpendicular component, and this x-perp is called the lever arm vector or momentum vector. Square of the lever arm vector is quite important when we study some rotation. X-perp is because the x parallel is n and hat dot x, parallel component along the axis of rotation. So we square this, expand x squared minus 2 times n hat dot x and n dot x. So it is n hat dot x squared. If I square this, n squared. However, we have n squared equals 1 because it is a unit vector. So minus 2 and plus 1 results in this. What's that? This is a squared b squared minus a dot b squared. This is a squared b squared 1 minus cosine theta squared, and that is a squared b squared sine squared theta. This is a cross b's squared. Therefore, I can always express this x per squared as a square of n cross x. We simplify omega cross x. We restrict ourselves that n hat is invariant. It does not change at all. Omega cross x, omega is proportional to n hat, and x is decomposed into parallel component and perpendicular component. Cross product n cross n, same thing, cross product always vanishes, so we can ignore this. And the answer is omega cross x perp, and omega x and omega n hat is omega vector, so it is omega cross. Oh, that's fine. So omega cross x is omega cross x perp. As you can see, x perp. This is omega. This is omega n hat. Cross product with the parallel component always vanishes, so omega cross x is always the same as omega cross x perp. That is perpendicular to the axis of rotation. If I make use of the back-cap rule, x cross this one. What's that? N hat cross x perp that we just have evaluated. So this back-cap rule can be applied. BAC dot minus CAB dot back-cap x n hat and C x perp minus. Okay, so I can produce this because n hat at x perp, they are perpendicular to each other, so I can ignore n hat x perp. Where is n hat x perp? Okay, this is x is this one should be x perp. So I missed perp in here. Okay, so this one and hat the x perp is a 0, so I can remove this. And x dot x perp, x is sum of x parallel and x perp, scalar product x perp. These two are perpendicular to each other, and dot x perp vanishes, so only x perp squared survives. So this is n hat x perp squared. Wait a second. This is x. Sorry about that. I missed that point. N, that's fine. X, that's fine. X perp minus x perp x n hat. It was not x perp. Sorry about that. So we do the calculation, and here I have n dot x perp plus n hat x perp. So that n hat that x. Okay, and this one vanishes, but this one does not vanish. So hence this one is this term becomes x perp squared. That's fine. This form becomes that's it, x parallel. If I read n dot n hat dot x vector, if I multiply this as 1 times n hat dot x, I cannot reduce it anymore. So this is the complete form. The total orbital angular momentum can be computed. Sum of differentials, element at point x, and momentum. That is a linear momentum. Linear momentum is mass times velocity. And we have x is here, velocity is here, mass element. If the rigid body is rotating about omega, that is parallel to n hat with a fixed axis, then velocity is omega cross. And omega cross can always be expressed in terms of omega x perp, because n hat is proportional to omega. The parallel component vanishes completely. So if I substitute this one in here, then we have a triple scalar product. Finally, we have a triple scalar product expanded in this kind of form. And the first term is x perp squared mass, and the other term is rather complicated. However, if we restrict ourselves to a planar form, that is the flat form on the xy plane, then x is always perpendicular to the axis of rotation. In that case, we can ignore this. Finally, angular momentum is expressed as, what's that? X perp squared dm integral. That is moment of inertia. If we make use of moment of inertia, I can make use of this moment of inertia multiplied by angular velocity of the rigid body to obtain the total orbital angular momentum. If a rigid body is in equilibrium, total linear momentum is 0, and total angular momentum is also 0. If they are both 0, its time derivative is also 0. Therefore, the net force and net torque on the rigid body must vanish.